Welcome to this lecture in the new series of lectures in group theory. Today we'll be looking at the notion of the greatest common divisor of two integers, and let us recall what we need to know in order to understand this lecture. So let us recall the definition of division. If we have two integers a and b, then we say that a divides b. This is the notation for a divides b. If first of all a is non-zero and that there is some integer q such that b is a times q. So that's the definition of division, and this is how we express it in notation. And then there are these synonyms that a divides b, same as saying that b is divisible by a, same as saying there is a factor of b, same as saying that b is a multiple of a, and so on. And we also have seen this theorem about division with remainder, that if you have two natural numbers, then there exist unique integers. Although what I had written was correct, but this is what we really stated, so I'm restating it. So there exist unique integers q and r such that these two conditions happen. So this was division with remainder. Alright, so these are two exercises. We extend our division with remainder for the dividend being not just a positive integer but an arbitrary integer, and you get the same conclusion. Nothing changes. And in this one we even extend our divisor to be an integer, but note that the conclusion here is somewhat same, but one has to be somewhat careful. So this would be a most general form of the division with remainder, but really the heart of the thing is the thing that we stated. And you can prove these using this. You don't have to go over the proof again. You can just use that statement to prove both of these. All right. So first let me define what is a greatest common divisor, and then we will see a theorem about it, and that will be it for this lecture. So suppose we have two integers and not both of them are 0. So one of them can be 0, but not both of them can be 0. We are assuming that not both of them are 0. So then an integer d is called a common divisor if first of all it is non-zero and it divides both of them. So it is really what common divisor means. It's a divisor that is common to both. So that's what the definition of common divisor is, as simple as that. And the greatest common divisor of a and b is defined as the maximum natural number that is a common divisor of both a and b. So collect all the common divisors of a and b, throw away the negative ones, and take the maximum. Basically, you don't even need to throw away the negative ones, just take the maximum of that set. So that's what greatest common divisor is, and that is the notation GCD. This is how we write GCD. Great. So let us see some very simple examples which I leave as an exercise for you. So show that this is the case for all natural numbers. Show that GCD of a and b is at most, is at least 1, and it is at most the absolute values of both a and b. So this is again for all integers a and b, not both 0. And lastly, for any two integers a and b, not both 0, we have all of these equalities. So these are exercises. Please solve them. Very easy to do. Okay. So this is a very important lemma that will play a key role in the next lecture, and it is very interesting in its own right. So suppose we have two integers, not both 0, and suppose we have b written in this form, b is equal to cq plus r, and I do not insist that r is in this range or any such thing. It's just some equation where c looks like the divisor and b looks like the dividend. I do not insist that the remainder is in some range or anything. Okay, great. So then the claim is that GCD of b and c is same as the GCD of c and r. Right, and this can be very useful. So suppose you have some big integer b and then you have some other integer c and you want to find the GCD. You apply division with remainder, then you get cq plus r equals b. And here r is strictly less than this guy. So basically what will happen is your computation will be reduced to computing the GCD of some smaller numbers than you started with if you apply division with remainder. But here in this theorem, we don't even insist that R is satisfying any such range. Anyway, so let's prove this. So let alpha equals, whoops, what is this? Alpha equals GCD of B and C, and beta equals GCD of C and R. So then, since alpha divides B and alpha divides C, because it is the GCD of B and C, so it divides both, we have alpha divides B minus CQ. So perhaps I should have given this as an exercise also, that if alpha divides something and alpha divides something else, then it divides the sum of the two things, it divides any integer, quote unquote, integer linear combination of the two things. So I hope you see that if alpha divides B and alpha divides C, then it divides this number, and you can immediately prove this using the definition. Okay, maybe next time I will give this as an exercise just so that it is for the record basically. Anyway, so please take a note of this, and this implies, and this is exactly the same as saying that alpha divides R. So therefore, alpha divides C and alpha divides R. So we started with these two things. Well, alpha is the GCD of B and C, so we started with these two things, and we ended up showing that, in fact, alpha divides C, which is already there, but moreover, alpha divides R. Therefore, alpha is a common divisor of C and R. It's a common divisor. And therefore, by definition, alpha is less than equal to the GCD of C and R, because GCD is the greatest common divisor, so any common divisor will be at most the greatest common divisor. Similarly, you will get that beta is less than equal to the greatest common divisor of B and C. Exact same kind of argument. But what is GCD of C and R? GCD of C and R is, this is equal to beta and this is equal to alpha. So now if we look at these two inequalities, alpha less than equal to beta and beta less than equal to alpha, we conclude that alpha equals beta. And that's it. This is what we wanted to show. We wanted to show that this GCD is same as that GCD, and that's what we show. Great. So we have shown this. Let me mark that, the Helmholtz symbol. And now there's a very simple consequence of it, that GCD A comma B is GCD A comma B minus A. This is for all integers A and B, not both of them are 0. So this is because A equals B plus A minus B. This is B times 1 if you want to write it that way. This is B times 1. So this gives us that GCD of, by the previous lemma, we get GCD of A comma B is GCD of B comma A minus B. But GCD of B comma A minus B is same as GCD of, I don't have space. This is equal to GCD of B comma B minus A. Right? Just note that this is equal to that, and this is what I also stated here. Okay, so that's the reason why these two things are equal. So let us finish this lecture with this small problem. It was asked in the 1959 IMO. This was the first problem in it. 1959 was the first time IMO was introduced to the world. This was the first ever problem in the first ever IMO, and it's a very simple problem. asks to show that for any natural number n, this GCD is always 1. So let's show this. So by the previous corollary, GCD of the given thing equals GCD of, well, let me also say this in the previous corollary. I can also write this. It's the same thing. You can argue this also. As we argued this, you can immediately argue the same thing, because this equality is also achieved by the same kind of equation. Alright, so we'll use the second one. We'll use this one, this guy, and that gives us 21n plus 4 minus 14n plus 3, comma 14n plus 3, which is equal to GCD 7n plus 1, comma 14n plus 3. And okay, so I'll flip the two things. It doesn't matter, I'm just doing it in a very sloppy or rather snail manner. So all I did was just change the order of the things here. So again, I apply the previous thing. I get 14 plus 14n plus 3 minus 7n plus 1, comma 7n plus 1, which is GCD of 7n plus 2, comma 7n plus 1. And I apply that once again. So we get 1 comma 7n plus 1, and this is obviously 1. So that's it. That's the proof of this small problem. So just take a note of these things, and you can get variations of this. This is not the only way to state this corollary. There are other things you can cook up of similar nature. Doesn't matter. Okay. So yeah, this is all for this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.